So this will be now the next video. We're going to do the ball bearing idea. So I was watching the Robot Studio on YouTube. I watched all of his videos recently. I just binged them all, and he uses a lot of small bearings inside like the joints. So he'll have one bearing on either side of like the index finger right here, then one on either side of the index finger here. And I was like, man, those are some small bearings. I didn't even know they make them that small. And he had a part list under one of his videos where it lists like the actual size of the bearings. I saw how he typed it out, and then I searched that and I bought some. But while I was at it, I asked ChatGPT, are there like other bearings of this size ballpark, like even smaller than this, but kind of in the same ballpark? And ChatGPT was like, yeah, you can buy 1 millimeter by 3 millimeter by 1 millimeter. I'm like, what? Is this a typo? Like, ChatGPT must be malfunctioning. You know how it can make up stuff at times. So I Googled that for bearings and I found it. I was like, what? That is so small. Like, it was insane. I mean, think about how small that is, guys. It's insane. So I was like, okay, that could make a great pulley. So I got that and a couple other sizes for my robot. And I'll tell you the sizes right now because this is important. I want to have some options for testing and whatnot. So let me just pull that up. I just bought them a couple days ago. All right, so 1 millimeter by 3 millimeter by 1 millimeter ball bearings. I bought 100 or 200 of them on AliExpress for $25. So that's super cheap. 2 millimeter by 5 millimeter by 2.5 millimeter ball bearings. I bought 200 at AliExpress for $43. And then I also bought the same size the Robot Studio is using in the fingers, which is 3 millimeter by 8 millimeter by 4 millimeter miniature ball bearings times 30. I bought on Amazon for $24. So the real tiny ones, 1 by 3 by 1, I bought 200 of them for 25. But the 3 by 8 by 4, I bought only 30 for 25. So the real tiny ones are a lot cheaper. 200 for only 25. That's a super good price. I think that's like 10 cents each or something. 12 cents each. So that's very reasonable, and we're using 12 per pulley. So at around 10 cents each, that's $1.20. So it'd be like $1.50, $1.60 per motor then for the down gearing system if you're using that kind of bearing. And then maybe the more expensive bearings, maybe double that or triple that. So you could be looking at like $7 per motor to down gear that motor. And that's assuming you're down gearing it like 64 to 1 using 6 pulleys. Plus you might need like 1 or 2 pulleys to like make certain turns to get to your pulley system. You might want to do that. If you're making some 90-degree turns, you don't want to do that within the Teflon tube because it might rub on the Teflon tube over time and rub through the Teflon tube. I'm not sure if 90-degree turns are safe to do inside Teflon tubing or if you should have it exit the tubing, go around a bearing, and then enter the tubing again for making 90-degree turns. I'm not sure which way to go or which one will be necessary. I'm not positive. But definitely the Teflon tubing can give you like less than 90-degree turns. I'm just not sure if 90-degree turns is too aggressive to do inside the guidance tube without it rubbing on the tube too hard as it's actually, especially for like the stronger motors where there's a lot more tension in that string. So that's that. That was a mouthful. So for the bearing design, to make pulleys out of bearings, it's so cool. So basically the bearing looks like this. Okay. And then what I wanted to do, okay, so we know we're going to have rope coming down and around the circumference of the bearing that comes up from the top. And we know we're going to put a rope through the bottom and tie it off, and it's going to come down to the bottom. What will keep that rope from sliding off the side since it wants to walk laterally and fall off the bearing? We need some kind of flares, some kind of wings on here that's taller, like some washers or something. And I figured it out. So basically, like some hard plastic would work great. Um, like hard, stiff plastic. You guys know how, like, if you buy a pocket knife or something on Amazon or at the store, it will come in like a lamination plastic, like a stiff packaging. You have to use a knife to cut through it to get your product out, and it's like a clear plastic, and it usually has it, let me draw what the plastic looks like. You guys will all know what I'm talking about. So like, let's say you bought like some product, and it's like a pocket knife or something. You'll just see the knife and the product like that, and then at the top it has that super famous little tab like that, and then at the store it'll have like a pin going through it on the shelving. The pin goes through it like that, and you'll be able to see the product in there and read about it. And there'll be like a bunch of graphics in here, like a sheet of cardboard in it. That type of plastic, whatever that is, that would be perfect for what I want to do. So I have to like harvest some of that the next time I see it, or look around the house for something of that similar quality that's like kind of stiff, but it has some flex. Kind of like the same plastic of like a 2 liter pop or a water bottle, like something like that material, um, but thin and kind of stiff and just really smooth. So that's what we want. And basically, we will cut it out and put it around either side, just kind of sandwiching our bearing. And then it essentially looks like a bobbin. It will look like a bobbin at that point. But how are we securing that to the bearing? I thought about that a lot. Like, this is so small. Like, the distance from here to here is 1 millimeter. The height is 3 millimeters. The distance of here to here is 1 millimeter. That's how small this is. So how you can't like caulk it on or something. Like, how do you join these? So I was thinking, I got it. I will put a thread string with a sewing needle, and I'll thread it through. Like, I'll stick it through. It'll come through, and then it'll come through, and then I can tie it off, and then I'll have a couple strings left. So I would sew it on where it's pinched on by some string that goes all the way through both of them with a sewing needle, and then I thread it through again, and then I just tie it off. That simple. And these could be pulled tight. And since they're nice and flat, they'll just be snug, but not too snug that they would interfere with the rotation of the actual bearing. So that there'd be a lot of friction. It wouldn't be that tight, but it'd be tight enough to keep the string from walking off the bearing. So then you'll have your string actually apply after that. Comes down, and then it comes through, and then it comes back out. Like that. We added our string now, and then these do not rotate, mind you. They stay stationary, these ones. So then through here, we put, only thing that rotates is the actual outer race or whatever it's called in the bearing. And we put our other string through here, and come out. Now we don't want, okay, since this string meets down in like a V, we don't want it to be too much of a V taper, because then that would pull the bottom parts of the flare of that plastic we added. It will pull that toward each other, which would cause the top to open up and create a little crack, which this string could walk into and then mess it up. We don't want that to happen. So we got to make sure that there's enough standoff, like right here. Maybe we could even put like a little tiny piece of tubing or something right here before we tie it off. Or just make the knot thicker in that spot. we could probably tie the knot in such a way that this angle where it comes down and meets in the center, if it's not as thick, then these ropes will be like more parallel to each other. We want them as parallel as possible, so it's not like messing with our flanges that we added. So those plastic flanges are the only modification we make to the actual bearing. And we only need to thread a string through once, then thread it back through, and then tie it off in order to adhere these flanges to it. And if we need to, we could put we could put rope through the bottom flange and then through this flange and then back around as well, so that the bottom side is pinched a little more, so that this rope can't walk out and press on the flange and open up the flange a little bit, even though this rope is kind of pulled taut and keeping the flange from opening that way or that way. So we don't want this rope that comes down and through to be able to walk off or press the flanges out of the way and get into here, and then it'd be like the rope would be going through here and rubbing on this rope, and it'd be off the bearing at that point. So we want to make sure that this stays trapped on the outer circumference of the bearing. That's very important. And so that's the bearing design, a modified bearing that turns the bearing into a pulley in a very simple way. And all of this can be tiny, tiny, tiny scales. So we can have lots of little pulleys, since we need a lot of pulleys to down gear 64 to 1 down gear. And we won't need any gears to achieve the 64 to 1 down gearing ratio. And like I said, 12 cents a bearing, $1.50 to down gear. So that's the magic plan. And since this is 3 millimeters in diameter, then this would only be like 4 millimeters in total diameter. So it's going to be a tiny little piece of plastic we're cutting out, and it shouldn't be thick at all. Just a very thin little piece of plastic. And so that's that. Those are the two pulley designs. Well, I'm in the second video. I talked about the other pulley design in the last video, but it's on one recording. I can show you guys the 4x8 by 4 millimeter pulleys, which I did buy. No, it's 3 millimeters by 8 millimeters by 4 millimeters. And by the way, when it rips it out like that, it's the first one is the diameter of the opening. The second one is the total diameter of the whole pulley, and then the final one is the thickness of the pulley, or the height. If you were to lay it flat like a pancake, it would be the height. And so here's the pulley. You can see here's it compared to a X-Acto knife blade for an idea of the scale. Everybody that does robotics and stuff knows what an X-Acto knife blade looks like, so that should be a good scale comparison. Okay, I just lost that bullet. Or a standard big pen, you know how big that is. So this should give you an idea. That's very small. And this one's the biggest one I bought. The other two are significantly smaller. This is 3 by 8 by 4. I bought 1 by 3 by 1 and 2 by 5 by 2.5. So this will be my big boy. This will be probably, I think, the biggest one I'll need. But you can find out what they're rated for on some websites. I might show you, as far as like how much crushing force can they have on them and stuff, which kind of scares me to think that they can be crushed in my system. So I might need these for like bigger motors, like the biceps or something. Mainly focused on the arms. So like for the arms, this would probably just be for the biceps. I probably wouldn't even need ones this big for anything else. Bicep, tricep would be probably this size maybe. But I might even be able to get away with one size down for that. And the way the Archimedes down gearing pulley system works anyways, as you get near the 64 to 1 ratio, that's where the most force will be placed on a pulley. But like the pulleys above that are just downloading at like 2 to 1 gear ratio, 4 to 1, 8 to 1, those will be dealing with much lesser forces. They'll just be moving faster. These can handle any speed pretty much. They handle like 104,000 RPM, no problem. So we're not even near that. So basically, we would maybe just use the bigger pulleys near the bottom of our Archimedes pulley system. And I'll just show you guys the Archimedes pulley system one quick time, since you guys might not have seen my videos on it, just as a quick review. So that's like this. So the string comes through the top, it goes around, it goes back up, it goes through, it goes around, back up, ties off. And then, so these two guys would lift up as the string pulls, and then they'd pull this one up, which then also lifts up. They pull this one up, and this one up. And these are both also the same exact system. So this shows it before, is they're all stacked here on the bottom, and then this shows it after it's fully actuated. So this side turns into this side. That's before, after. And so the bottommost one, you see it raised up that much, so the string will pull total that much. And I think these only go about this high, but I'm not sure. They might go a little bit higher. But the point is that these two moved way up here, so they move the most. And then this one doesn't move as much, this one doesn't move as much, this one doesn't move as much, this one doesn't move as much. So each one moves a little bit less, but has way more force put on it. That's how it works. That's the whole principle of it. And also, this first pulley achieves a 2-to-1 gear ratio. This achieves a 4-to-1. This achieves a 8-to-1. This achieves a 16-to-1. This achieves a 32-to-1. This achieves a 64-to-1 gear ratio. So ChatGPT really helped me to find tiny, tiny bearings. I didn't know they exist this small, so that's why I was trying to make my pulleys designed just as wraparounds, just a little plastic disc in the middle, and then just wrap around it, and they would just rub through this Teflon tubing. And I thought that rubbing would be fine, but later I just got kind of paranoid. What if it's not fine? What if it rubs through the tubing by way of the friction and the braids on the rope, rubbing and rubbing? What if it just wears right through that tube within like 1 day of use? Then that would be like too high maintenance. Like you have to replace every pulley every day. That's ridiculous. So that may not happen. I mean, maybe with proper greasing and blah blah blah, maybe it would work, but I'd feel a lot more comfortable for sure just doing it right, like more ideal on actual ball bearings, which are really designed for like long-term, lasting a long time, whatever. They'll last as long as my motors that way. So that's the update.